So let's talk about arc length parameterization. Arc length parameterization. Ways of taking the idea of how far have we traveled on our path and normalizing the velocities to be all of them be unit vectors. I want to have traveled 1 unit in 1 time unit. 1 unit of distance and 1 unit of time. And in order to do this, we're going to utilize our arc length function. Now, our arc length function measures how far have we gone in time t. And I'm going to just define a brand new function that will readjust our inputs and our time in order to speed us up or slow us down in such a way. What I want to define is a new function. So we have function r. We have r of t is our path. I want to define a new r theta of s that will be the same path, except the speeds will be adjusted. And I don't use this s willy-nilly. This s is actually going to be our arc length. As I travel 1 unit, I want my distance traveled to be 1 unit. As my inputs go by 1, I will have traveled 1. As I go too far, or by 2, I will have gone 2. So all of my speeds will exactly be 1 by 1. Now, in order to relate my s's and t's, I'm going to need to define a new function. I want to define a new phi such that phi of s of t is actually equal to t. I want the inverse function of s. We happen to have that s is invertible. S is an always increasing function. So there does exist an inverse phi. And so this phi is going to be this new way of adjusting my inputs that I can relate s back to t. And so here, phi being the inverse of s. In order to find a new parameterization for our arc length, I need to calculate the inverse of my arc length. So, step being, in order to find this, first we start with our r. We calculate our arc length s. We calculate the inverse of s, phi. And then, when we're done, our r prime of s will be our r of phi of s, which is r of t. Right. So we end up with the same functions, changing our inputs to be such that they fit our idea of having unit length, giving us unit time. So let's write down our process for finding arc length here. When actually computing this, we're going to take r of t, our vector value function, calculate the arc length, s of t, arc length, find phi, the inverse of s, and then take r of phi of s to be our new parameterization. So let's do this on an example, one that I've cleverly manipulated to have nice numbers. Let's take our r of t to be sine of 2t, root 5 times t, cosine of 2t. Should probably recognize this as some sort of helix traveling in some sort of direction. We're now going to calculate what our arc length of this would be. So we have that s of t will be equal to the integral from 0 to t du. And the velocity vector of this, the magnitude is going to be 0 to t, the square root of all these derivatives. Derivative of there we got n squared. 4 sine squared 2t plus that squared will be, derivatives first. Derivatives first. R prime t 2 sine 2t.
Cosine.
Negative. Cosine.
Negative.
And root 5 and sine. 2 sine. 2t.
No, negative.
Derivative of cosine is sine.
Negative sign.
Derivative of sine is cosine. Derivative of cosine is negative sine.
Yeah.
All right, killing it here. Nice. Magnitude is the square roots squared. 4 cosine squared 2t plus square root 5 squared is 5 plus 4 sine squared 2t. Here we got cosine squared of something plus sine squared of something. After you factor out the 4, we'll leave you with 1 there. 0t 4 plus 5 plus du. And we get the integral from 0 to t of the square root of 9 is 3 du, which should be 3t. So s of t will be the integral from 0 to t of 3 du. We got 3t. We can easily calculate the inverse of this. The inverse function of 3t will be s equals 3t. Inverse will be phi equals s over 3. So r of phi of s will be r of s over 3. And we just plug into our original function here. S on n 2t over 3.
Yeah.
S. Square root of 5 times s over 3. Cosine 2s. And if you check, the speed of this will always be 1. There we go.
That's great. So today, so far we've talked about calculating the arc length given a vector valued function. We've also talked about an arc length function where you can input a time t and get out a arc length, how far you've traveled so far given that time t. And then finally we used all of those pieces to come up with an arc length parameterization, which is a reparameterization of our original r of t, so that our speed is constant. Here our speed could be all crazy all over the place. This time our speed was a constant of 3. And we reparameterized it so not only is the speed constant, but it's a constant of unit 1.